So now we will do basic operations based on these signed and unsigned numbers. So in computer system, basically it understands the 0 and 1 combination. So whatever representation is there, either signed numbers are there or unsigned numbers are there, we will be representing a number. Basically, if it is a signed number, then to represent a signed number like a number is negative, basically we will be using the 2's complement, because 2's complement is based between the other sign representations like sign and magnitude representation and 1's complement, because also it is having a single representation for 0, and also this 2's complement requires, like in terms of hardware, it requires less number of hardwares for implementing the 2's complement. So basically we will be going to know if we are requiring any negative numbers, we will be using 2's complement. If we are going to work on positive numbers, we will be basically working on the normal binary number or in 2's complement itself. So here we will see, like if we are going to perform arithmetic and logical operations, or basically the arithmetic operations on different types of numbers, then how we should be performing these operations, like addition, subtraction, multiplication, and division, basically. So these are the basic arithmetic operations. So we will see different types of arithmetic operations and what different algorithms we will be using to perform that particular operation. So in terms of representation, we will just recall, like suppose we are having 83. So if we want to represent 83 and minus 83 in terms of 8-bit representations, then we will just see. So in case of plus 83 is there, so it is a decimal representation. So if we want to convert it into a binary representation, then we should be making sure like we can just subtract the 2 to the power maximum value of 2 to the power that can be there. We can do like that. Or another method is we will be dividing 83 by 2, and then whatever the remainder comes out, starting with from the downward, we will be moving to upward, and that will be representing our binary representation. So this is a decimal representation, and this result is a binary representation. So this is about the plus 83. And if a positive number is there, the same representation will be there in all the cases, like either is sign magnitude representation, or it is 1's complement, or it's 2's complement. In all the three representations, the plus 83 will be represented by like the same only. But in case of minus 3, each of the representation will be having different representation. So in terms of minus 83, so in sign magnitude, so this is the value that is 83. So if we are going to represent in sign magnitude, the first will be representing, the first bit will be the sign bit. So here it is minus 83. So first bit instead of 0, it should be 1. This is the sign. And all the remaining bits, these bits will be the same. So only sign bit will be 1 for a negative number if we compare with unsigned numbers. So it is plus 83, minus 83 will be in sign magnitude representation, it will be 1 and then the same magnitude value. In 1's complement, it will be like we need to take the 1's complement of the positive number. So if it is minus 83, if we want to convert it into minus 83 in 1's complement, then first of all we will be writing plus 83, and after writing plus 83 we will be taking 1's complement of plus 83. Then the number that will come out, that will be the 1's complement representation of minus 83. Similarly, in case of 2's complement representation, if we have if we want to represent minus 83 into 2's complement, then first we will be representing plus 83, and then after representing the plus 83 in binary, we will be converting it into binary, and then we will be taking the 2's complement. So after taking the 2's complement, whatever the number will come out, that will be minus 83. So this is the basic method we will be following for representing a number into different representations of sign representations. Okay, so 3 representations there. So we will be writing like that. So similarly, in case of sign magnitude, the only change is the sign bit is changed. So instead of 0, we should be writing 1. Similarly, in ones complement, whatever the binary representation is there, we are going to convert each bit, or we are going to complement each bit to make it ones complement. So ones complement is simple. So if 0 1 0 is given, so its ones complement is given by like each bit we will be complementing. So if it is 0, we will be complementing it to 1. If it is 1, we will be complementing it to 0. If it is 0, we will be complementing it to 1. So this is two. This is ones complement representation of 0 1 0. So we will be complementing it. So it is 1, so it is 0. It is 1, so it is 0. 0 0, so 1 1. So after that 1 is there, so it will be 0. If it is 0, it will be 1. If it is 1, it will be 0. If it is 0, it will be 1. So here, in case of ones complement, we are not going to change the sign bit. We are not just complementing the sign bit. We need to complement each of the bit of the binary representation of positive number to convert it into ones complement. That will be a negative number. In case of twos complement representation, the same we will be doing is whatever for converting to twos complement, we have two different methods. One is ones complement number, whatever is coming ones complement, and then we will be adding 1 to this ones complement. Once we are going to add 1 to this complement number, ones complement number, it will be coming out twos complement. So we can just see here. So if suppose the ones complement number is this one, so we are going to write it here 1 0 1 0 1 1 0 0. If we add 1 to this, whatever the number will be coming out, that will be the twos complement. Okay, so it is, we are going to add it. It is 1, this is 0, this is 1 1 0 1 0 1. So this is nothing but the twos complement. You can just compare it here. So it is the twos complement. So this is the basic conversion of any number. So because this we will be using again and again, so you should be clear with this representation. Suppose another number is there, like convert this into a decimal integer in all four representations. Four representation means unsigned, signed, ones, and twos complement. So this is the number. Okay, so we are going to convert it into unsigned, signed, and these four different types. So if it is this number is there, whenever there is like 1 is there, so we will see what is the weight of each of the digit. So this is 2 to the power 0 is there. This is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. Similarly, up to 2 to the power 7. So wherever there is 1, we will be writing it. 1 is there, 2 to the power 7 location is 1. So 2 to the power 7 is 128. So here it is, this one is representing the 2 to the power 6. 2 to the power 6 is 64. So it is plus 64. This is 32. This is 16. And then this location is 2 to the power 3, that is 8. But 8 is 0. So we will not be adding it here. Again, this is the location of 4, 2 to the power 2. 2 to the power 2 is 4. We will not be adding it because it is having the value of 0. Then 2 to the power 1, that is converting it to the power 1, that is 2. We will be adding it because it is 1. This is 0. So 2 to the power 0 is 1. We are not adding because this is a 0. And then we will be adding it. That will be its unsigned magnitude representation in decimal because we are going to convert it into decimal number. Next, suppose this is a signed magnitude. So if we are going to convert it into signed magnitude, then we will be thinking of this number as it is a signed magnitude number. If this is a signed magnitude number, then whatever the MSB bit is there, this is 1. That means 1 means signed bit is 1. It is implies that the number is a negative number. So this is the negative, and the remaining bits will be considered as the magnitude. So the remaining bit will be considering as the magnitude. So last MSB bit is having a weightage of 128, and then it has come to 242. When we are removing this weightage, we need to subtract 242 minus 128. So we will subtract 242 minus 128. If we are doing that, it will like 12 minus 4, that is 12 minus 8, that is 4. This is 3 minus 2, it is 1. It's not. This is 3 minus 2, that is 1, and then this is 1. So once we subtract this, the remaining value that is coming out, so this will be the representation. So sign magnitude representation will be magnitude value will be this, but the one that was starting that is going to say it is negative, so it will be converted to minus 140. Similarly, if we are going to convert it into ones complement, so if this is a ones complement number, we need to think it as a ones complement number. If it is a ones complement number, we need to convert it into decimal equivalent. So because it is 1 at the MSB, it will be showing like the number is a negative number, and then its magnitude will be coming out by like changing its ones complement into taking the another ones complement. Whatever that value will be, that will be coming out into two binary representation. So this number is now ones complement. We will be taking ones complement, then so 1 1 1 1 0 0 1 0. So ones complement will be just complementing each bit. So 1 0 1 1 0 0 0 0, and then this is the ones complement number. So its magnitude we need to find out. So it is like converting ones complement. It is coming out into binary. So normal binary is there. So 8 plus 4 12 plus 1 13. So 13 is there. This is the magnitude, but its sign will be decided by the previous number, that was this one. So this was having the MSB as 1, so its sign will be negative, but its magnitude will be 13. So in ones complement it is minus 13. Similarly, in twos complement, this number will be considered as the twos complement number, and if it is twos complement number, we will be taking again the twos complement, that will be giving out the magnitude, but the sign bit will be representing the sign, that is 1, that is negative. So it is negative, but we will be taking its twos complement. Once we are going to take the twos complement, we will be adding 1 to this number, then it will be like a twos complement. Once we are going to add it, it is 0 1 1 1 0 0 0 0. So this is the twos complement. After taking the twos complement, this is the number that will be in binary. Its equivalent will be in decimal is 14 in decimal. So this 14 is magnitude, and its sign will be with respect to this 1. So this is minus 14. This is how we can convert it into a number to twos complement. So next we will see is addition, like how we will be doing the addition. So in case of computer system, computer only understands the zeros and ones. So 0 1 0 1, whatever representation is there, the computer will be understanding only this. So we need to perform the addition in terms of zeros and ones, or we need to perform the subtraction in terms of zeros and ones. Similarly, we need to perform the multiplication and division also in terms of zeros and ones only. So the basic, in case of addition, so the basic addition what we do is, suppose 1 2 is there. In case of decimal number is there, and it is suppose 15. So what we do is, while doing the addition, we just take it like 19. Okay, so once we are going to add these two number, decimal number system. So 9 plus 2 is 11. So once it is 11, after adding these two number, 11 is coming. So out of this 11, we will be taking 1 here, and 1 that will be considered as the carry, and we will be moving it here. Okay, so again we will be adding this 3. So 1 1 1, that is 3. 1 plus 1 is 2, plus 1 is 3. So it is 31. So this is the answer. Similarly, suppose we have another number. This is the number we are going to add. So what we do is, 9 plus 4 is 13. So 13 is what it is coming. So once it is 13, we will be writing 3 here, and 1 we will be writing here. And then 8 plus 3 is 11, plus 1 is 12. Once again it is 12. So out of 12, we will be writing 2 here, and 1 will be coming out here. So again 7 plus 2 plus 9 plus 1 is 10. So when it is 10, out of 10, we will be writing 0 here, and then 1 will be coming out as a carry to the next column. Okay. So 6 plus 1 plus 1, that is 8. So we will be writing 8. So this is the result after addition. Similar approach we will be adopting for adding the numbers in terms of zeros and ones. So if it is a number is there, suppose this is the number. If this is the number, we are going to add it with this is the number we need to add. So once we are going to add it, again we will go with the same concept. So we will be starting with the right side addition. So 0 plus 0 is coming out to be 0. So we'll be writing 0. If it is 1 and 1, so when we are adding 1 and 1, it is going to come out like 1 and 1 we are going to add, it will be coming out 2 in decimal. If it is 1 and 1 in binary, once we add it, it will be coming out to be 2. 2 after addition in decimal, but its binary equivalent is 10. So after adding 1 its binary equivalent is, this is decimal and this is the binary. So binary is 10. So out of 10 we need to put 0 here and 1 will be coming out into the next column, similar to the decimal addition. Similarly, this 1 plus 0 plus 1 we will be adding, so it is again coming out to be 1 and 1 will be in decimal, it is 2. So 2 means 10. So again it is 10. So 0 we will be putting here and 1 will be putting here into the next column. Again we will be adding 1 plus 1 plus 1, that is coming out to be 3 in decimal. So here 3 is in decimal, but in binary 3 is this one. This is 1 is the 3 in binary. So here we need to write in binary. So we will be putting 1 here after addition, and this extra 1 will be coming out to be into next column. So it is 0 plus 0 plus 1 is 1. 1 1 is coming out to be 10 because 2 in decimal, 10 in binary. So it is 10. So this will be the result after addition. So this is how we should be proceeding with the addition. But we can just go through it. So here you can just see if the possibility is sum of the two digits. So sum of the two digits if and in any in carry in is there, any carry in is there, and then adding these two numbers. If it is coming out after summing this, if it is coming out to be 0, we will be writing 0 and carry will be 0. So this one that we are writing, this one, these are called carry, and this is carry in means before we are going to start the addition, whatever any other carry is there from outside, that will be considered as carry in. So in this case carry in is 0. So here when carry in plus adding two digits are coming out to 0, we will be writing 0, we will write here 0 and carry is 0. Similarly, if we are having the sum is 1, so if sum is coming out to be 1, we will be writing here 1. So in this case, like here in this case 0 0 and 1, if it is this is the case, 1 is coming out to be sum. So 1 is the coming out to be sum, so this is the 1, we will be writing 1 here and carry will be 0. So carry was 0, that's why we have not written anything. Summing two digits, we are going to get sum as 2 in decimal. So 1 and 1 we are getting 2. So 2 is equivalent to 10. So for that we will be writing write 0 here and carry will be coming out here. So this is how the basic addition takes place into the binary representation. There is an example given, you can proceed with it. And another example is like if there is no here no carry was there, but here after adding the numbers we have got a carry, that is carry means initially we have taken the bits like 1 2 3 4 5 6 7 8, 8 bit first number, 8 bit second number. After adding the result we are getting the 9 bit, 8 bit this one and 1 is this one. So this is coming out to be carry. But if we are having only 8 bit register, then we cannot store the result after adding whatever the result is there, that is coming out to be of 9 bits. But we have registers that stores the result that is of only 8 bit. So in this case we can say like it is having a overflow. So overflow, when overflow will come, we are having two mug. We are having two mugs. Okay. But we are having we are putting some water into these mugs. If we are able to fill this mug with the water and water is not coming out of this after completely fill, so we will be calling it like no overflow is there. But when we are putting the water inside this jug such that the water is flowing outside because it has been full, once it is full the water will come out. So in that case we will be saying like it is an overflow is there. So that is the same. If we are having 8-bit register and if we are able to put values of 8-bit, so maximum value of 8-bit is coming out like all the ones. So 4 1 and 4 8 ones are there, so it is coming out like FF in hexadecimal, or it is like 255 in decimal. So if it is 255 in decimal, we can store up to 255 only. But suppose a number is there that is more than 255, or if there is a case like we are adding such that after addition we are having another output, that is carry output. So this carry cannot be adjusted into this 8 bit. Then also we will be calling it like there is an overflow, because we cannot accommodate 9 bits into 8 bit register. So that's why it will be calling like overflow. So we will see like how the overflow should be coming, or what should be the condition, so that we will be calling like there is an overflow. We will see into the next slides. So next is subtraction. So this is the subtraction method. So basically there are two different subtraction methods. One is the normal method that we basically do by taking like when we need to subtract, like suppose 24, we want to subtract 12 from the 24, we will be subtracting directly 4 minus 2, that is 2, 2 minus 1, it is 1. That is the basic one. Next is suppose it is 210 is there, and we want to subtract like 2, we want to subtract 109. Suppose we want to subtract 109. So when it is, we are going to subtract 1 minus 9, it is not going to subtract. So we need to take the borrow from here. So it will be coming out like 10 will be taking the borrowing. So it will be 11. 11 minus 9, it is 2. Then it is 0 now. 0 minus 0 is 0. Then 1 minus 1 is 1. So this will be the result. So here the borrowing concept is used. So similar is the case we can take in case of binary numbers also. So we have suppose 1, 1, 0, we want to subtract, and we want to subtract 0, 1, 1. Suppose we want to subtract this one. So here from 0 we are subtracting 1, we cannot subtract it. So we should be taking the borrow. So once it takes the borrow, it will be taking the borrow is like 2 will be the borrow. Here in case of it will be giving out, so it will be giving the borrow such that it will become 2. So once it is 2, now 1 minus 2 minus 1 will be coming out to be 1, and here it will be 0 again, because it has taken given the borrow. Now it will be asking for borrow. Okay, so again from here we are going to take the value. So once it is 2 again, 2 minus 1, it is 1. So after this will be the result. So this is equivalent to 6, and this is equivalent to 3. So 3 minus 6 minus 3, it should be coming out to be 3, and this is the 3. So this is how we can do the subtraction in binary also. Or there is another method. So this is the basic method. Second method is, what we can do is, second method with the help of addition. So it's like suppose a is a number, b is another number. We want to perform a minus b, and this should be the result. So in that case, instead of subtracting, what we can do is, this is minus b, we need to do the minus. Okay, so what we can do is, we can do addition, a plus minus b. This will be coming out to be c, and this will be the result. So here we are going to perform the addition. We are going to perform the addition of the number, that is a, another number is minus b. So we know like any number we can represent it into its negative value or sign representation. We have seen sign magnitude, 1's complement, 2's complement. So generally we use the 2's complement method to make a number negative. So suppose we want to subtract 36 minus 19. So we can do that by 36 plus minus 19. So we will be converting this 19 into minus 19, and then we will be adding 36 and minus 19. So this minus 19 will be represented by the 2's complement. So this 36 will be the positive number, the same whatever the binary number is there, 2's complement will be the same. But in case of this number, we will be using it with the help of 2's complement, and then we will be adding. So after addition, what will be the result will be there? That will be the subtraction value. So this is how we do the subtraction in case of binary representation. You can just see here the example. So we have already seen this example. So this is nothing but the same only. So in that, there is no carry is coming out or no borrow is coming out at the end. But here, after doing the subtraction, so subtraction is basically done like this is the number, another number is this one. So to subtract this number, what we have done is, we have converted, or we have taken its complement. So the first number is the same, we have written this only, but this number we are writing like we have taken the 2's complement. This is the 2's complement representation of this number. So this number is like 0 0 1 1 0 0 1 1. So once we take the 2's complement, first we will taking its 1's complement. Okay, so we will taking the 1's complement and then adding the 1. 1's complement is 0 0 1 1 0 0 1 1, and then we will be adding 1, that is 1 0 1 1 0 0 1 1. So this is the 2's complement representation. So this is nothing but the same 11001101. So once it is 2's complement, it is the negative number now. So whatever the number this was there, we have just converted into its negative value. So once it is in negative value, we will be adding these two. After adding, we are having a carry. So this carry, in this case, we are not saying like this carry will be an overflow. Not it is always like once we are going to get a carry, it will be representing an overflow. In the previous case, we have got a carry, so we said like it is an overflow. It is an overflow. But here, if a carry is there, we will not be saying this is not an overflow. So how we should be representing this overflow? Just see the overflow rules. So basically here, in case of overflow rules, if it is an unsigned numbers, so in case of unsigned numbers, we are going to do the addition. Then a carry out to the leftmost bit is also an overflow. So that means if an unsigned number is there, suppose 8 is there and 10 is there, or 8 is there and 7 is there. When we are going to add these two numbers, so it will be 15. So this 15 is there. So this is nothing but the carry here. Carry out, we can say. Okay, so this is a carry. So in this case, we can say like it is an overflow because 15 cannot be represented by one digit. Or you can say like, suppose 2-bit, we are saying like 10 and 11. This is the number. We want to represent it only in two bits only. So if we are going to add it, so 11 is coming out to be 0, then a carry. 11 is coming out to be 0 with a carry. So this one. So after adding these two numbers, we are getting the result into 2 bits only because we have 2 bits register, suppose. Then there is an extra bit. So this extra bit will be the overflow. So in case of unsigned magnitude additions, whatever is the carry out at the MSB side, that will be considered as an overflow always. This is the first one. Second, in unassigned magnitude subtraction, overflow will occur in subtraction if we must borrow prior to the leftmost bit. So if we are going to borrow in the case like suppose 10 is there and we want to subtract it 11. So here we are going to subtract, then it will be taking the carry, borrow. Once it takes the borrow, it is 2, 2 minus 1 is 1, then here it is 0. So 0 minus 1, it is not possible. So it will be taking a borrow from outside. If it needs to take the borrow outside from the outside, then it will be coming 2 minus 1. So it is here, that is 2 minus 1 is 1, and then there is a borrow. Borrow bit is 1. So this borrow is taking the outside from the outside. So in this case, we should be calling it like it is an overflow. So if it is going to take the borrow in case of subtraction from the leftmost bit, so this is the leftmost bit or the second, whatever this is the bits, MSB bit in both the cases. So if MSB requires a borrow, then that will be considered as an overflow. This is in case of unsigned magnitude subtraction. Similarly, in 2's complement, or you can call it like signed case. In 2's complement case of addition and subtraction in both the cases, if this is the important one, we should be taking care of it. If the two numbers have same sign, if the two numbers have same sign bit, the sum and difference has different sign. If two numbers have same sign and sum and difference have different sign, then there will be an overflow. This is the case in case of 2's complement representation. So if two numbers are there, if both the numbers have same sign, suppose this is the number, another number is there like 101. So in both the cases, like both the numbers have same sign, both the numbers have same sign. If we want to suppose add it, after adding we just see the result. So 10 is 1, 11 is 1, 1 is 0, and then carry, that is this. So in this case, just you can just see if two numbers have same sign bit, this is the first condition, it is met. Then the sum or difference has a different sign. So different sign you can just see. So this was having the same sign, that is 1 1, but the after summing the result is having 0. 0 is a different sign. So when it is having a different sign, if it is 1, then there is no carry, no overflow. But if it is 0, that means the two operands are having the same sign, but the result is having different sign. In that case, this 1 will indicate the overflow. This is what it says. Similarly, if you say the another example is like suppose 0 1 0, okay, 1 1 0. If this is the case, we are adding, this is 0, okay, this is 1, we are adding basically 1 1 is 0 with 1 carry. This is 1 1 and 1 1 is 0 with a carry. So in this case, you can just see, first of all, for the overflow, there must be like the two numbers should be having the same sign bit. But here the sign bits are different. In case of two operands, sign bits are different. When sign bits are different, either we are doing subtraction or addition, there will be no overflow. So this one is going to say like no overflow. So you should be taking this condition. So if two numbers are there, both should be having same sign first of all, and its result should be having a different sign. Then there is an overflow. So you can just see the results in the cases when there is an overflow and when there is a no overflow. So when there is an overflow, then whatever the result we have got, that is not the correct output. So in this case, after addition, this is the result 0 1 1. So this 0 1 1 is not the correct output. So here again we will see, if it is we are adding 4 plus 2, we are getting 6. So if we are getting 6, you can just see in case of here we are getting 6. So here there is no carry. Carry is not generated. So if there is no carry, no overflow will be there. If it is no overflow, then the result that is there, that is a correct result. If it is 4 plus 6, 4 plus 6, we are getting like we are going to add it. So after addition, we are getting the result is this one. So if this is the result, you can just see it was 0 and this is 0, and now we are getting the result like 1. So the result is coming out once it is 1. If it is in 2's complement, we are talking about the 2's complement. So if it is of 2's complement, it is a negative number, because this is a negative number. We will taking the complement, 2's complement, then what will is its magnitude will be there, like we are going to take the 2's complement. It is like 0 1 1 0. So this is going to give the 6 in decimal. So this 6 and this 1 bit will be minus 6. It is going to represent the negative. So minus 6 is there. So if it is minus 6, because this is plus and this is plus, but result is minus. So if result is minus, then the output, the sum or difference has different sign than the previous one. So previously we are having positive, positive, and this is negative. So it is having different sign. So there will be, and also there is no carry, but there is an overflow. Okay. So here, if two numbers have same bits, a sign bit, the sum and difference had different sign bit. Even if there is no carry, you can just see the special case. If there is no carry, also there is an overflow. If there is an overflow, the result is not correct. It is an incorrect result. No. Similarly, we are having negative 4, minus 2. Its result is minus also. If it is having same sign, if it is same sign and there is a carry also, if it is same sign, there will be no overflow. Okay, and if there is no overflow, the result will be correct. You can just see minus 4, minus 6 is there. The result is plus 6. In case of 2's complement addition we are doing, we can just go through it. So it is coming out to be plus 6. So when it is coming out to be plus 6 and there is a carry and also there is a overflow. Why? Because the inputs are having negative signs, both the same sign, but the output is having different sign, that is plus 6, plus sign. So there is a difference. So this condition is satisfying. So there will be an overflow. So when there will be an overflow, the result that is there, this is not the correct result. So it is a incorrect result basically. So whatever the result we have obtained, this is an incorrect result. So this is the case of overflow in case of addition and subtraction, when we are going to do the addition or subtraction based on the binary representation. So next we will see the multiplication and division. So starting with the multiplication. So in case of multiplication, if you do in case of decimal number system, so suppose a decimal number is there, 1 2 3 is there, we are going to multiply with 1 and 2. We want to multiply, then what we do is we start with the, this is called multiplicate. So yes, multiplicand. So this is the multiplicand, and this is called the multiplier. So whatever the result we will be getting after this, that will be your product, because we are multiplying. So this is your product. So for the result, we can see. So when we are going to have the multiplication, we basically do 2 multiplied by 3, that is 6, and 2 multiplied by 2, that is 4, 2 multiplied by 1, that is 2. Then again we will be multiplying with this 1, the same. So each digit of multiplier is going to be multiplied with the multiplier. So in this case, we are multiplying is here. So 3 into 1, that is 3, 1 into 2, 1 into 1, 1. And then whatever is the coming result, we should be adding. So if once we are going to multiply with the second digit, we have shifted one location to the left side. Once after multiplying, whatever the result is coming out, we have shifted it. So now we will be adding 6, 7, 4, and 1. This is the product result basically. So this is the case in case of binary, in case of decimal multiplication. The similar case we can adopt for the binary addition also, binary multiplication also. So if once we are going to multiply the binary numbers, so this is the number. So the only difference is in case of binary multiplication, the easiest way is like whenever there is 1, we are going to represent the whole number again. When it is 0, we are going to represent one bit right, left shift, and this 0 0 0. Again it is 0, then we are going to make it 0 0 0, and again we are shifting another bit. When it is 1, we are writing the same, the multiplicand we are writing, multiplicand is writing, but we have shifted it again. So again it is 0, so we have added with one shift as 0. Then 1 is there, we will be going to multiply with this, and the same multiplicand will be coming out. So we will be shifting it again, and then we will be adding it, and that will be the result basically. We can perform the similar case in case of similar to the decimal multiplication, or we can show, we can represent this multiplication further with like that. The same is like once we are going to multiply, this is the multiplicand is same multiplied by the multiplier. This is the multiplier. So now what we are doing is, first of all, this is the multiplicand is same. Then whatever is, wherever this multiplier is 1, we have multiplied to that one. So we are multiplying this one and with the multiplicand, plus here it is 1, so we will be neglecting these 2 bits. Okay, so we are going to, or in terms of like zeros are there, so if it is 0 is there, so 1 2 3 4 5 bits are there. So leftmost bit we have ignored, so 1 2 3 4 5 bits. Again it is 1, so 1 0 0 1, so it is 1 2 3 4 bits are there. So again in third case we will be multiplying with this 1 and 0 0 0, plus the multiplicand is same, we have multiplied with 0 0 0, then plus the multiplicand plus 0 0, plus the multiplicand the same, and then the last one. After doing this, whenever there is a 0, it will be 0, it will become 0. So whenever there is an 1, that all will be added. So basically once we are going to multiply it, it is nothing but it is going to shift basically. So this multiplication is what basically it is going to do is, it is going to add such that it is going to multiply such that it is going to shift it basically. So after multiplying and then adding the result, we will be getting the product. We can do like that also. So similar concept we can implement in case of the algorithm. So basically instead of multiplying and shifting, we can make this into an algorithm. So that algorithm for multiplying is given by like that. So here this multiplication algorithm will only work if both numbers are positive. So this is an algorithm that will only be working if both the numbers that we are going to multiply is positive numbers. If we have negative values in 2's complement, we will use a different algorithm. If we are going to multiply two numbers that any of that number is negative, we should be using another algorithm. In the next slides we will see. So currently this is the algorithm basically for the positive numbers only. So you should be taking care of this. So in terms of the algorithm, you can just see. So the first will be like start. So after starting, there is a statement box. So in statement box, basically we are going to initialize. We are going to initialize this different registers. So in that there is an A register. So this A register is an accumulator. So basically we are going to perform with the help of processor. So we should be considering the registers related to the processor. So here A is the accumulator and C is the carry. This is basically the carry out. It is of 1 bit. C is of single bit. Okay, and A is an accumulator. So accumulator length or the register, whatever the bits will be there, that will be decided by the n value. So this n is like if a multiplier is there, m is the multiplier, or sorry, m is the multiplicand and q is the multiplier. So in this case, so suppose m is of m, that is multiplicand, is of suppose 0010 and q is of 1100. So in this case, multiplicand is of 4 bit and multiplier is of also 4 bits. So multiplier and multiplicand should be of same bits. Okay, and whatever this bits is, that is 4. So if 4 bit is there, then we should be putting n is equals to 4. We should be putting n is equals to 4. If it is n is equals to 4, we should be taking the accumulator also of n bits only. So accumulator will be of 4 bit. Okay, and this C is always like C is the 1 bit register, you can say 1 bit it is storing basically. So this is called the initialization part. So basically we are going to do the initialization. So once we have initialized, so because in this case, once it is 1 2 3 4 5 6, multiplier is of 6 bit. So when it is 6 bit, we need to multiply this into 6 times and then we should be adding. So that's why this, if whatever the number of bits available to multiplier and multiplicand, that should be of same, and also the multiplier and multiplicand should be having the same bit, and that bit values will be the n value. That means at that time the loop should be repeating itself. Okay, so this is the C is the single bit storing the carryout of the addition of A and M. So basically in case of accumulator content and M, we should be adding, because accumulator is initially initialized to be 0, accumulator is 0, and multiplicand, so we should be adding, because this final that we have got is we are adding the multiplicand. Okay, we are adding the multiplicand 3 different types. So how many types we should be adding and what shift we should be providing, that we will be getting to know here only. So based on that only we should be going to repeat this for this loop in n different types. So n will be the number of bits of multiplicand and multiplier. So C is the carry out after adding A and M. After adding A and M, whatever the carry will be there, that will be restoring into C. And then we will be checking here Q0. So Q0 is there. So suppose Q is there, this one. So this, if it is Q, that is of 4 bit. If it is of 4 bit, then this will be the Q0. This is the Q1. This is Q2. This is Q3. So similarly, once we will be proceeding, we should be checking for Q0 whether this Q0 is 1 or not. If it is 1, that means we should be adding the A and M. So if it is 1, if it is satisfied, it is yes, then we should be adding the A plus M. A is starting with 0, A is content 0 is there, M content is the multiplicand, so we should be adding multiplicand and the accumulator, and it will be storing into A accumulator. And at that time, this is the C. After adding, either the result could be of 8-bit, or if it is we are talking about 8-bit, so in that case the result will be either 8-bit or there will be a carry. So carry will be stored into C. Then it should be going to next step. In the next step, we should be shifting. Basically, it is right shift C, A, and Q content. C, A, Q content we should be shifting right, and also we should be decreasing the value of count, that is the number of bits, by 1, and then we should be checking whether the count is 0 or not. If the count is not 0, if it is not satisfying, we should be again going to here and we should be checking the Q bit, because we have shifted this right side. This Q bit has been shifted to the right side. Once it is shifted to the right side, this Q1 is now, once it is shifted, so here it will be a 0, and then it will be Q3, Q2, and Q1. So now Q0 we have used, we have one times we have multiplied or whatever we have done. Now we should be checking for Q0. So this is now the Q0. So now we should be checking the Q0 location. Either it is 0 or 1. Based on that, we should be selecting. If it is 1, we should be proceeding this way. If it is not 1, we should be proceeding to just shifting. And then we should be checking again, like what is the count value. If it is not 0, we should be again moving and then again checking the location of Q0. So this shift is basically going to make it like all the multiplier bits have been counted in all the number of loops. So if it is 4-bit, 4 times the loop will be repeating. So all the 4 bits like 0, 0, 1, 1 will be counted for multiplication or for directly right shift. And finally, the result will be stored into accumulator and the Q content. So after the end of the operation, the product will be stored into A and Q also. So A, that is accumulator, and Q will be storing the overall result, because if it is a 4-bit multiplication, so the maximum result that we can get is of 8-bit. So we have 4-bit multiplication, or it is n-bit multiplication is there, then the result will be of maximum 2 n bits. Okay, so one n bit will be storing into Q, another n bit will be storing into the accumulator, because both are having n bits in case of generalized case. Okay, so this is the algorithm for multiplication. This is the basic algorithm for positive numbers only. So we can take the example of it. So just proceed it here. So in terms of example, we will be first, suppose yes. So the first is like we should be having a carry. For carry, 1 bit storing, it should be storing 1 bit. So once we go with this initialization step, initial values will be like accumulator will be 0, 0. Suppose for an example, Q we have taken is 1, 1, 0, 1. If Q is 1, 1, 0, 1, that is, this is the multiplier, and this is the multiplicand. This is the multiplicand. So at the starting, we should be placing the value of multiplicand into M, multiplier into Q, and accumulator, that is A is 0 and C is 0. So in the first step, we have initialized that, and also the count value. So we can just put here the count value. So suppose this is the count value N. N is initially, because all are of 4 bits. So N value will be 4 initially. So once we have initialized, we should be now proceeding to the next step, that is Q, checking for Q naught. So this is the Q naught value. So this is always like, if this is the Q value, so this will be Q naught. This is Q1, Q2, and Q3. So it should be checking for Q naught. So Q naught is coming out to be 1. So if Q naught is 1, we can just see if Q naught is 1. If yes, then we should be proceeding in this way. We need to add accumulator plus multiplicand, and we should be storing into accumulator. Okay, and also into the C if there is a carry. So we should be basically adding A and M. So this is A is 0, and this is M. So we should be adding in the next step. Once we are going to here, check this is if it is 0 is there, sorry, if it is 1 is there, we should be adding this value and this value. So once we are adding, so the first step will be add. So once we will be adding, after add, the accumulator content is 1011 now. Whatever the multiplicand content is there, after addition, this will be there. So once we added, this Q value will be same, M value will be same. The next case is there. Once we have added, we should be going to the next step, that is shift CAQ. So we are going to shift content of C, A, and Q to the right side. So again, the second process in the first cycle only, we have the shift. So the content of C, A, Q will be shifted. So you can just see the C content is being shifted. That means we are going to shift this C content into here, this one into here, this is here, this is here, this one is coming out to be here. Okay, and this one will be come out here, 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 and this one is vanished. This one is basically vanished, or you can write like flushed. It is kept outside. It is flushed because it is already used for multiplying. So it is flushed now. So after shifting, this is the value of QA, and the M value will be the same only. So this is the first cycle. After shifting, we need to count. So count is like initially count is 4. So we need to perform 4 minus 1. So 4 minus 1 will be stored into count. This is the count. So count is initially 4. Now it is 4 minus 1. So once it is 4 minus 1, we should be doing it here. After this, the value is 4 minus 1. So it is, that is 3. So when it is 3, once it is 3, we should be proceeding to the next step. Now we need to check the count value. Either count is 0 or not. If count is not equals to 0, if it is not satisfying because it is 3, once it is 3, we should be proceeding to here. And again, we will be checking the Q naught value. So we need to check the Q naught value. Okay. So again, we should be checking the Q naught value. So Q naught value is here is 0. When the Q naught value is 0, because this is the Q naught value. When the Q naught value is 0, when the Q naught value is 0, if it is yes means it is 1. If it is no means it is 0. When it is 0, we will be going here and do the right shift of CAO. So in this case, if it is 0, we should be doing only the right shift. So in the second cycle, we will be not adding it because it is not 1. It is Q naught value is 0. So we'll be only doing the right shift. So it is right shift means now this was the value. Now we will be shifting it again. So this value will be here. This is here. This 1 is here. This 0 is here. This 1 will be coming out here. This 1 will be coming out here. This is here, and this is here. This 0 will be flushed out. Okay, so now this is the content of C, Q, and this is A, and this is C. And after shifting, we need to reduce the count by 1. So once we reduce the count by 1, now the reduced value of count is 3 minus 1, that is 2. Next, we will be proceeding to this stage. At this stage, we will be checking whether count is 0 or not. If it is not 0, if it is no, we will again go into here and check for Q naught. Once it is 2, it is not equals to 0, we will be checking again for 2, for Q naught. So Q naught we will be checking. So this is the Q naught again. Q naught in this time is 1. When it is 1, Q naught is 1, we will be doing the A plus M. Okay. And then again, we will be shifting and reducing the count value. So again, if it is 1, we should be adding. Now the add will be done. So add will be here is basically M plus this one. So add is here is like just we will be adding is like 0010 added with 1011. So once we add it, is 1, 1, 1 is 0 with a carry, and this is 1, and this is 1. So there is no carry is there. So all the values will be like 1101. So 1101 will be stored here at A, and the carry is 0. So carry is added to be 0. And this C value is put as it is when add was performed. So after addition, we will be doing the shift. So we will be doing the shift operation. So we will be again shifting it. So here, this is shifted to here. This one is shifted to here. And again, this one is coming out here. This one will be left out or flushed out. So now after shift, this is the case. After shifting, we should be checking like we should be reducing the count value. So now 2 minus 1 will be like 1. So now the count value is 1. When the count value is 1 and it is not equals to 0, then again we will be moving to check for q naught again. We will going to loop into. So we should be checking for q naught. So in this case, the q naught is again 1. So when it is 1, we should be performing the add operation and then shifting and then count reducer. So here, once it is 1, we should be again adding. So adding is 1, 0, 1, 1. So it is 0, 1, 1, 0. This is a value, and m value is 1, 0, 1, 1. So we will be adding. So this is 1. 1 plus 1 is 0 with a carry. 1 plus 1 is 0 with a carry. This 1 plus 1 is 0 with a carry. So here 4 bit will be in A, but this 1 bit will be stored into C. So this C will be, once we are adding, C will be here stored in 1, and the result will be 0, 0, 0, 1. So 0, 0, 0, 1 will be in A, and C will be as it is copied here, and M will be copied again. So once after adding, we need to perform the shift operation. So shift will be, we will be shifting it here. And this will be flushed out. Okay, so after shifting, this is the value. So at that time, once it is shifted, it will be checking for, like, it is going to reduce the count value. So count value is 1. Now it is count value is 1 minus 1 is 0. Once it is 0, it is going to check either count value is 0. If it is yes, if this time it is yes. So if it is yes, it is going to end. Now the end will be there. So once it is ended, at the last, the result, that is the product value, will be stored into the content of A and C. So this will be A and C. So the result is 1, 0, 0, 0 and 1, 1, 1, 1. So this is the result of 8 bit. So for storing the product, it should be requiring 8 bit. Okay. So need 8 bit location to store the result of 2 4 bit multiplication. So this is the basic multiplication in case of multiplication algorithm for 2 positive numbers. So this is one of the algorithm. So another important algorithm is there for multiplication, that is called Booth's algorithm. So basically, in case of the previous algorithm, it has the limitation like it can only multiply the positive numbers. Similarly, there is another multiplication algorithm that is called Booth's algorithm. This Booth's algorithm will be used basically either for multiplication of numbers such that either one of the number is negative or both the numbers are negative. Then we will be using the Booth's algorithm. So we will just go through it, like what is the Booth's algorithm. So in the similar case only, here we have not considered the negative signs in case of multiplying here basically. But in the second case, we will taking the multiplication such that the sign of the multiplier and multiplicator will be considered. And also the advantage of Booth's algorithm is it requires less number of hardwares. It requires less number of hardware. So hardware is here in terms of addition and number of multiplier and additions, or basically the number of additions required. Number of additions required. So in terms of hardware, we are talking about ALU is there. So basically in ALU, we are shifting and adding. But in case of Booth's algorithm, basically, even if it is going for negative number multiplication, then also it is going to reduce the complexity of the system, and also it is easy and fast than the previous algorithm, and also it requires less number of hardware. So we will be proceeding further. Is like, suppose this is the start, and then after that we should be considering the accumulator that will basically be initialized to 0, and here q minus 1 is there. So this q minus 1 is like, suppose if q is there, we have seen into the previous one. So q is basically, suppose it is a 4 bit. In case of 4 bit, the q will be like q0, q1, Q2 and Q3. This will be the Q. But there is an extra bit, that is Q minus 1. So Q0 is there, then Q minus 1 is coming out to be this one. So Q minus 1 is a bit. If it is 4-bit multiplication, basically, then there is an extra bit for Q, that is minus 1. Q minus 1. So Q minus 1 is initially 0. Q minus 1 is initially 0. So we should be checking the condition whether Q0 and Q minus 1 is either 0, 0, 0, 1, 1, 0 or 1, 1. So if it is 0, 1, if Q0 and Q minus 1 is 0, 0, 1, then we should be doing A plus M multiplication, A plus M addition, and then storing the result into A. And then we will be doing the arithmetic shift. Arithmetic shift right. So we have already gone through arithmetic shift right. So in case of arithmetic shift right, basically whatever the sign bit is there, that is copied while shifting the right side. So we should be shifting A, Q, Q minus 1 such that the sign bit of A will be remaining at the same, and the same sign bit will be copied to shift the right side. So we'll see once we go with the examples. Okay. So again, if it is Q0 and Q minus 1 is 1, 0, then we should be doing A minus M. And when Q0 and Q minus 1 is 1, 1 or 0, 0, we should be performing no addition and subtraction. We will just doing the arithmetic shift right. And then we should be checking for the count, whether the count is 0 or not. If it is not 0, we should be repeating the same. If it is 0, we should be ending the operation. So here M will be standing for multiplicand, Q will be standing with multiplier, and the count again will be having the same n value. This n will be the length of multiplicand or length of multiplier, or same length of multiplicand and multiplier will be having the length of A, that is accumulator register also. So again here we are going to take an example in case of Booth algorithm, and then we will see like how we can proceed by solving the questions or basic questions related to the multiplication in case of Booth's algorithm. So in this case, you can just see. So here A is the accumulator, Q is there, and there is an extra Q minus 1 bit, Q minus 1, and this M is multiplicand. And at the initial stage, initialization stage, basically the Q minus 1 will be 0, accumulator will be 0, and Q will be the multiplier. So Q is multiplier, that like 0, 0, 1, 1 is there. So this is equivalent to 3. This is plus 3. But in case of multiplicand, you can just see like the result is 0, 1, 1, 1. Okay. So this is the result. So this result is nothing but the value that is stored into here. So once we are going to store the value, so if we talk about the value, basically here M value, so this M value will be storing the negative value. So this negative value will be like the 2's complement. So this is a 2's complement. So once it is 2's complement, okay, so once it is 2's complement, we will just see if it is a 2's complement value, it will be like, if first of all it is 0, 1, 1, 1 is there. So if it is 0, 1, 1, 1 is there, that means it is a positive number. So again here also it is going to make it, it is basically going to take the positive numbers only. It is not going to take the negative numbers. We can take the negative numbers also. So with the help of negative numbers also we can proceed with the solution. Just for an example, we can just see like here we are going to multiply 3 into 7. So once we are going to multiply 3 into 7, the result should be plus 21. So plus 21, if we write it into binary case, so the product should be in binary is like, first of all, if it is 4-bit, 4-bit, multiplication result will be of 8-bit. So in that 8-bit, we need to represent 21 into 8-bit. So 21, for representing the 21, we should be writing like plus 21, suppose we are writing. Then 18, sorry, the 16 we should be writing 16, and then 16, after that 3 will be there, so 16, and then 0, 16 plus 5 will be 21, so 16 plus 1, 0, 1, this is 5, 8, and this is 16. So this is the 21, and this is 4-bit, 5-bit, 6, 7, and 8-bit. So this is 4-bit like 0, 0, 0, 1, 0, 1, 0, 1. So this is the result in case of plus 21. So if it is plus 21, this will be the result. So after end of the operation, we should be getting the result this as the output. If we are going to multiply with two positive numbers, so we can use the negative numbers also. But for an example, we have taken like how the Booth's algorithm is working. So we have taken the two positive numbers. So this m is a multiplicand, that is 7 plus 7, and this is the multiplier plus 3. This is the initial values. So to start with here, and also the count value, because it is a 4-bit representation is there. So the n value or the count value should be initially 4. Now we should be checking for q0 and q minus 1. So q0 is this one and q minus 1 is this one. So it is 1 0. So when it is 1 0, so when it is 1 0, when it is 1 0, we should be making like a minus b. We need to write the a minus b. So first of all, this is the plus m. If we want to find out the minus m, then we should be taking the 2's complement. So when we are going to take the 2's complement, its 2's complement will be like 1 0 0 1. So this is the minus m value. Okay, because we have taken the 2's complement. So this is m value. So when we are going to do a minus m, instead of that doing minus, what we can do is we can add a minus m. So once we need to perform a minus m, we can do like a plus minus m. So it is a is initially 0 0 0 0 plus minus m. Minus m is nothing but 1 0 0 1 1 0 0 1. So once we will be adding, the result will be like 1 0 0 1. So this is the result into a. So now after the first point, it should be checking the value of q0 and q1. It is 1 0. When it is 1 and 0, it should be doing the a minus b, a minus m. So once it is going to do a minus m, it will be storing the result into the value of a. So a is 1 0 0 1. Okay, and then the value will be copied here all. So it is going to do a minus 1, a minus m. So after doing a minus m, it should be going to the next stage, that is arithmetic shift right. A, q and q minus 1, it should be arithmetically shifted. So from here to here, we should be shifting right side. It is arithmetic shift right. So once we are doing the arithmetic shift right, whatever this a is there, this is will be considered as a single data. When it is considered as a single data like 1 0 0 1, then q value is 0 0 1 1, and then q minus 1 is 0. So when this is the value, we are going to shift it right side. This is arithmetic shift right. This is the sign bit, and this sign bit is 1. So this sign bit will be copied the same, and whenever we are going to shift it, this sign bit only will be shifting. So this will be the same. This is going to shift it here 1. Then this is going to shift it here 0 0 1 0 0 1 1, and this last one will be like vanished or flushed. It will be flushed. So up to here we should be considering. So here this the value of, if we talk about, so up to 4 bits, so up to here it will be a, up to here it is q, and this last bit is q minus 1. So you can just put this value. So it will be coming out like 1 1 0 0, then 1 1 0 0, then 1 0 0 1 1 0 0 1, and at the last q minus 1 it will be 1, and all m value will be the same. After shifting, we should be getting the result like that. After shifting, the next is we need to reduce the count value. So we need to reduce the count value. So count value is 4. So now after reduction, the count value is 3 now. After reducing 1. So again, once we have reduced, we need to check the count value. If it is 0, but it is 3. If it is not 0, we should be moving again to check for q0 and q minus 1. So at this, we should be checking the value of q and q0 and q minus 1. So q0 is this value and q minus 1 is this value. This is 1 and 1. It is 1 and 1. So based on the algorithm, if it is q0 and q minus 1 is 1 and 1, 1 and 1, then we should be moving to this step, that is arithmetic shift right only. So we should be just performing the arithmetic shift right. There is no addition or subtraction. So in this case, we should be moving to arithmetic shift right only. So we are going to shift it right. So once we are going to shift it right again, we should be doing like the same. This value, magnitude value will be same, and again this will be shifted. Okay. This is how the shift will be done. After shifting, we should be checking for the count value. So if it is 3, we should be checking like it is reduced to by 1. So it is 3 minus 1, that is 2. Now the count value is 2. Now we will be checking the count value whether it is 0 or not. If it is not 0, we should be moving again to check for q0 and q minus 1. So it is 2, it is not 0. So we should be proceeding further to check for q not and q0. So again we will be checking like this is 0 and 1. So if q0 and q minus 1 is 0 and 1, we should be doing the addition. After addition, we should be doing the shifting. So now we will be doing the addition, that is a plus m. So after doing the addition, we will be getting the result like once we do the addition. So this is the a value, that is 1110, and the m value is 0111. So once we do the addition, it is coming out to be 1. This is coming out to be 1 and 1 is 0. Then there is a carry 1 and 1, 0 plus 1 is 1. There is a carry 1 and 1 is 0, and there is a carry. So up to this 4 bit will be stored into A, and this will basically coming out to be carry. We should be ignoring it basically if there is a carry, because it is A can store only 4 bit. So this is an extra bit, that is like an overflow. We should be not be considering it, ignore basically. So we'll be storing the A value by 0101. So next stage 0101 will be A value, and q value will remain the same because we have done the addition, we have not done the shifting. So the q value will be the same, q minus 1 value will be the same also, and m value will be the same. So once we have done the addition, now we need to do the shifting. So shifting will be like if 0 is there, so 0 will be continuing here only, and then because it is arithmetic shift, whatever the sign is there, sign will be remaining the same, and then we will be shifting right side. Okay. So once we have done the shifting, we need to check the value of count. So count is 2, so we should be reducing it by 1. So 2 minus 1, this is 1 now. And now we should be checking the count value. Count value is not 0, so we should be again checking with the starting. We should be continuing into the loop and checking for the 0, q0 and q1. So q0 and q1 is again 0 0. So if it is 0 0, we need to just do the shifting. So again we need to do the shifting by taking this 0 at stage and this shifting. And after shifting, we should be reducing the value of count. So after reducing the count value, it is coming out to be 0. Once it is coming out to be 0, we should be checking the count value, either it is 0 or not. If it is 0, yes, then it is end of the operation. So once it is end of the operation, whatever the result that is stored basically into A and Q, that will be the result here. So after addition, after multiplication, the result will be like this one. So this result is there, like A and Q value will be the result. So similar you will do for the negative numbers also. So any of the numbers you can take negative and do the multiplication, the result will be coming out the correct one. So this is the basic of Booth's algorithm. So up to here it is the multiplication. So these are the multiplication operations basically. The next operation is division. So in case of division, basically we are having two different cases. So there are two different methods to divide. So one divide method is called, or algorithm is called uh, restoring algorithm for division, and one is called non-restoring. So we will be seeing the both algorithms one by one. So there is a difference between the restoring algorithm and non-restoring algorithm. So basically in case of division, Restoring algorithm means it is going to restore the accumulator content what is previously were there to use the case of division, but in case of non-storing, it is not going to use the restoring property of accumulator. So this is the basic difference in terms of hardware and different operations that is going to perform. It is having the difference in that case also. And basically these two algorithms are basically for unassigned numbers. So basically when we are going to do the division, so whatever the basic division is there, suppose we are going to divide like 22, we are going to divide by 3. In that case, it will be going for like 7 times, and 1 will be the remainder. So this is the quotient, and this is the remainder. This is divisor. This is dividend. So next we will see after this division algorithm. So there are two different algorithms like restoring algorithm and non-restoring algorithm. Once we proceed with that, after that we will going through the floating point algorithm. Okay. So for today's class, that is okay. So thank you. From the next class onwards, I will be taking the division part, and then we will be going with floating point number. So I hope you have got the point, whatever we have seen. So in terms of multiplication, two algorithms we have seen. The Booth's algorithm, that is very important. So you should be taking care of it. And based on that, we should be considering. So also go through the advantage and disadvantage of these algorithms. What is the advantage and what is the disadvantage? What is the advantage in terms of what particular parameters, hardware, speed, circuit complexity? So these are the different concepts you should be going through it. So thank you. Then we will see into the next class.